Hey guys, this is the second video for section 16.3 on the fundamental theorem of line integrals. Hopefully if you're watching this you've already seen the part A video, which goes over what the fundamental theorem of line integrals is. Again, I'm abbreviating this FTLI. So we know how to use that theorem in order to take line integrals of conservative vector fields. Now, we've seen that that formula works super nicely. I can integrate things that look like gradient of f dot dr over some sort of curve C really quickly. You just evaluate at the endpoints and subtract. But there's kind of a catch. How do I know when the vector field that I'm integrating is conservative, right? Now, why this is potentially a problem, right? Before, pretty much all of the examples that I saw, most of my examples, these guys looked a lot like, I explicitly wrote out, hey, there's a potential function, here's my gradient, right? So now the reason that I'm posing this question is, what if I see something that looks instead a little bit like this? Right? So I just throw you whatever the heck the vector field is, and I don't give you the potential function, right? What if I see something like that? Now, the problem with this is that if I just have this vector field, it might not actually be conservative, okay? And the catch is, the fundamental theorem of line integrals only works with these conservative type things. It only works with vector fields that look like gradients. So if this thing doesn't happen to actually be a gradient, we actually are stuck kind of using old methods, right? So we can't necessarily use this fundamental theorem of line integrals in every single case. It fails to work if we're not conservative, right? So what this is telling me is I am going to need to find a way, right? So we need to be able to check if some arbitrary vector field that I give you guys, if this guy looks like a gradient, right? So does this thing look like my gradient of f for some sort of potential function f? Okay, and once you find that potential function, if it does exist, then you can go back and apply the fundamental theorem of line integrals to whatever your problem is, okay? Now, if you're wondering how to do that, here's the idea. I'm going to have us dust off a little bit of information that we ran into when we were first learning about partial derivatives, except for most of the nice functions that we encountered, the ones where they're twice differentiable and those gradients that not gradients, but those partial derivatives that we get back, they're continuous. For those kinds of functions that we run into, if you take a mixed partial, it doesn't matter which order you take these in. If your mixed partials are continuous, you can do them either way and you'll get the same thing back. So if you have to take fxy or fyx for a function of two variables, you get the same thing. Well, what I want to do is use that information to help me check for when I've got a two-dimensional vector field that I don't know if it's conservative or if it isn't. Okay, now to kind of develop this test, let's make the assumption that we actually do have a conservative vector field. What should I expect to see, right? Well, if I have that this thing is conservative in the first place, this is going to mean that there exists some sort of potential function, right? So there exists some sort of f of x, y, with, this vector field looking like my gradient of f, okay? Or another way that I can phrase this is this f should equal, if you've got a two-dimensional function, or two-dimensional vector field here, your gradient should have two components. These should look like an x partial and a y partial of whatever that, function is, okay? Got my x partial, got my y partial. Now, One thing that I'm going to go ahead and note here, if I apply this okay, is the following. The reason that I brought up the equivalence of mixed partials was this. Let's go ahead and see what happens if I take this first piece that I see in my gradient, and let's take a partial of this thing with respect to y. If I take a partial of that thing, specifically just this piece, I should get something that looks like, basically you do fx and then you do, a y partial, that should come out to fxy. On the other hand, if you look at this second component here, and instead of taking a partial with respect to y, we take a partial of that with respect to x, well, the result there, since we read this notation left to right, is that should give me fyx. And a comment, since we said that our goal is for my mixed partials to be the same, if these were the same exact function, well, these should come out the same if we indeed did start, with a potential function f in the first place, right? So if we indeed started with some f, okay, and then took a gradient to get my vector field. Now, for me to consolidate this, if you're not quite getting what I'm saying, here's what we're getting at, right? The assumption is if we are conservative in the first place, I kind of want my p to look like an x partial, and I kind of want my q to look like a y partial. Now what's going to happen is we have kind of a test that we can apply to check to see if that situation actually happened. Since you want your mixed partials to be equivalent, this suggests that when you are given a vector field that is two-dimensional, you've got some scalar function in the first component, some scalar function in the second component, I'm calling these p and q. What you want to do to check is you take a partial of the first one with respect to y, and you take a partial of the second one with respect to x, and if you get that though that equation actually works out, the left-hand side actually matches the right-hand side, you get a conservative vector field, okay? So, if this equation works out, yay, we're conservative. On the other hand, if this doesn't happen, where did I go here? Wrong page. If this doesn't happen, you're not conservative, right? So if you take these partials and you get two totally different functions, fundamental theorem of line integrals won't apply for your integral because you don't have a conservative vector field. We have to come up with some other method to integrate. Now, with that said, since we are in a section where we're focused on applying the fundamental theorem of line integrals, I want to show you guys how to do this, or, how to approach it if it is conservative, right? So let's assume we pass this first step here. You take those partials, everything checks out, you do have a conservative vector field. If you want to move forward, that means that you have to actually find your potential function. The fundamental theorem of line integrals requires that you know what that scalar potential function is for you to evaluate at the endpoints. So, step 2 is going to be actually integrate to find that potential function, right? Now, if you're kind of fuzzy on why I'm integrating here, or what I'm integrating, or what I'm doing, the idea, like we said before, is if p and q really look like fx and fy because this is a gradient, well, if this is fx, and I derive with respect to x, and if this is fy, and I derive with respect to y, right? So kind of what we're shooting for is you basically want to take, an antiderivative of p with respect to x. You're assuming this is the same thing as this antiderivative of q with respect to, let me get the right variable here, with respect to y, and this should come out to be whatever your function f is, okay? So this should be your end result. Now, with that said, be careful with kind of the notation that I'm using here. I know that we've seen these guys as line integral differentials before, so scalar line integral differentials, where I give you some curve and we think about this as dx dt. I'm not doing any of that. Now, you'll notice I don't have any c's here, okay, with these integrals, so here, you know, there are no c's. These guys really are partial integrals, okay? So we're taking, kind of like you do partial differentiation, we're doing partial integration here, okay? Nothing funky, just, you know, kind of the same thing where if I'm anti-deriving with respect to x, y acts like a constant. If I'm anti-deriving with respect to y, x acts like a constant. I'm not doing any weird differential switching here, just straight up anti-derive and look for a scalar function. And we're just going to try and see if we can reconcile that into one function. Now, in that case, if you actually do find your potential function for your conservative vector field capital F, what you want to do is just do a rewrite, right? Like if we realized that capital F is the same thing as gradient little f, we can rewrite our integral. And now, if I know that it's written in this form, this is kind of the perfect situation for us to apply the fundamental theorem of line integrals, okay? Where you plug in your endpoint of C and your start point of C to this potential function, and you subtract, okay? Now, I'm going to get started just with testing to see if we've got stuff that's conservative, so we're going to take a look at this example really quick here. Is this vector field a conservative vector field? If it is conservative, we'll go through the hoops that we just said that we would jump through to try and find the potential function, okay? So I'm not worried about integrating right now. I'm just worried about applying, you know, that test and that series of follow-up steps above, okay? Well, what we said is we wanted to check you know, for this situation where, you know, f is PQ. So here in this case, my scalar function e to the y, this is P, and my scalar function x squared, this is Q, okay? What I'm checking here is, does my partial of my first function, okay, dp with respect to y, does this match when I take my partial of my second function with respect to x, right? So again, I'm trying to see if this gives me that fxy, fyx behavior where these things match, okay? Well, let's actually try this. If you take dp dy, well, dp dy in this case is just e to the y. The derivative of e to the y with respect to y is itself. And dq dx, my second function, if I derive x squared with respect to x, I get 2x. You'll notice these do not equal each other, okay? So since that failed, if these guys are not equal, that means that your original vector field is not conservative, okay? So this was not what we were looking for. If you guys had ran into this particular vector field in a line integral, this means that you cannot use the fundamental theorem of line integrals to evaluate. You need to go with one of our other methods, okay? So at this point, you know, you would have to fix your bounds, your function, your differential. That would probably be the technique that we would need to integrate with this guy over some curve. Now, on the other hand, I'll give you guys a slightly different example. It's going to look really, really similar, but have a very different outcome. I'm going to go ahead and ask, is this vector field conservative? Now you notice I still got an x squared and an e to the y function, but I've put them in different component slots. So let's go ahead and see what happens here, right? So the thing that I am really trying to check, again, is if I view this vector field as some PQ, okay, my first scalar function being P and my second scalar function being Q, what I'm really asking here is, does my partial of p with respect to y does is match my partial of q with respect to x. Okay, again, because we are hoping for this to look a lot like fxy and fyx, and if they match, that means that there's some sort of f that gave me these functions in the first place. Okay, so let's actually grind through this here. If I try to compute dp dy, well, that p function was x squared. Your derivative of a function of x with respect to y is going to come out to 0, right? There are no y's here, so x squared acts like a constant. That means when you derive it, it's just going to drop off. And actually, we get kind of a similar thing going on over here for dq dx. Since your q function is this exponential e to the y, but I'm deriving with respect to x, there are no x's here, so e to the y acts like a constant, and you're going to get a partial derivative of 0. So that actually does check out, right? So since that does work, your end result here is that your f actually is conservative because that equation matched up. Okay, now we're not done yet, because I said not only to test is this thing conservative, I wanted us to find whatever the heck the potential function was that gave me this vector field in the first place, right? So now my big goal is going to be to find this f such that my gradient of f gave me this vector field. Okay, and the way that I'm going to do that is this. Okay, again, to reiterate, if my f is going to look like fx, fy, what I want to do is antiderive this first bit with respect to x, and then I want to antiderive this second bit with respect to y, and hopefully what I should get back is f, right? I need to reconcile what do the antiderivatives of each of these pieces look like. Okay, so let's actually look at this antiderivative of fx with respect to x, or this is kind of what I was saying before, my antiderivative of p with respect to x. What was that first function? Well, I'm going to scroll up real quick. That first function was x squared. Okay, so I'm really looking at my antiderivative of x squared dx. And this is going to give me x cubed over 3 plus a constant on the end. Now, here's kind of the catch, since these guys are all partial antiderivatives, right? What is happening here is these guys are partial antiderivatives. That means that I'm not treating these as single variable functions. I'm treating these as functions of x and y. If you antiderive with respect to x, that means that you possibly might have had some y's floating around that you got rid of, right? So I'm going to go ahead and note, yeah, you might get a constant on the end of integration, but that constant could have been a function of y, right? Now, if you're kind of like, what the hell is this? Why is this thing going on the end? I still don't get what she's getting at. Recall that a good way to check your work whenever you antiderive is you should be able to derive and get your original integrand back. Okay, now hopefully that makes sense now, because if we were doing partial antiderivatives, if you take a partial derivative to go in this direction, you know, if I derive this end expression with respect to x, anything in terms of y falls off because y acts like a constant. Okay, so that's all I'm getting at here, is there's some sort of y function on the end. Right now I don't know what that is, but we'll come back to that in a moment. Okay, now we just did the first bit, right? And I derive that first piece with respect to x, we get f back, but I also have to antiderive the second piece with respect to y, right? Now that means that I wanted to really take an antiderivative of this fy expression, or, you know, whatever the second component function was in your vector field, And if we scroll up, we'll see that function was e to the y. Okay, so here's my q that I wanted to antiderive. So if I'm antideriving e to the y with respect to y, I'm going to get e to the y. And same sort of argument that I just made above about my constant functions, I'm going to get some sort of constant function, this time of x, because I was antideriving with respect to y. If we want to check our work, you derive this expression with respect to y, you get your original integrand back. Okay, so deriving this with respect to y, that constant bit falls off. Now I said that we were supposed to get f back, and these look like two totally different functions. Now, here's where we need to kind of analyze the results that we got back. It might not be super obvious, but we did get f. Since we had established that this was supposed to be a conservative vector field, what really needs to happen now is I just need to reconcile this into one function, right? So just reconcile this into one function, f of xy. Both of these are really the same exact function. They're maybe just written in slightly different ways. Now, the way that I can reconcile this into one different function is this. Notice that I start out with, in this first piece, I had a function of x, but down here I also have a function of x. Well, the way to reconcile that is that these are really the same thing, okay? So both of those are functions of x. If I want to look at my functions of y, both of these guys are the same thing. So if I wanted to kind of rewrite this in terms of one particular function, what I could do is just use this potential function, f of xy, is instead of writing C2, actually write what we know C2 to be. Instead of writing C1, actually write what we know C1 to be. And then I'll go ahead and make note, if you want a general potential function, we can throw a plus c on the end, but for sake of us computing things, if you actually are trying to, worry about how your potential function integrates out, I'm going to go ahead and note, that for sake of applying fundamental theorem of line integrals, okay, for fundamental theorem of line integrals, yeah, the plus c gives you the most general answer, but if you're plugging in an endpoint and you're subtracting what happens when you plug off the start point, the plus c's are just going to cancel, right? You're going to have a c minus c in your expression, okay? So if you choose to write that in, if you choose to not write that in, I'm not going to be particularly picky about that, okay? So the reason that this guy is optional, this will eventually cancel out. You won't really need it in the end, okay? But if you're looking for a general answer, this is your potential function. Now let's actually see this in practice with an example where I'm asking you to integrate, giving you a slightly different and harder vector field to work with now. Let's see if we can apply the fundamental theorem of line integrals to actually evaluate this integral where I give you this curve parameterization, okay? So what I'm going to go ahead and do real fast here is I'm going to go ahead and check if this thing is conservative, right? So basically, again, what I'm looking for is, does my dp dy look like my dq dx? So if I look at my dp dy, hopefully we see that you're going to get, this thing multiplied by y here is a constant. I'm just going to hang on to that constant. The other term has no y's in it, so that's a constant. When you derive it, that just totally drops off. And what I'm comparing this to is dq dx. So the derivative of that thing with respect to x, well, chain rule says derivative of the outside, 1 over x plus 5, times derivative of the inside, in this case it's 1, so this actually does work out, okay? I probably wouldn't have explicitly asked you guys to use the fundamental theorem of line integrals on a problem where it wouldn't work explicitly. So here we actually get that my f in my integrand is conservative here. Actually is conservative. That means that what I need to do is find my potential function, right? So find that little f that I took a gradient of to get this thing back. Now, if I'm trying to antiderive this first piece, okay, this y over x plus 5 minus 3e to the 3x, that needs to be antiderived with respect to x. The idea is hopefully this looks like fx, so I undo the partial by antideriving. And then the other antiderivative that I have to take to try to reconcile my potential function is I have to antiderive this thing, my log function, with respect to y. Okay, so my log of x plus 5, I need to antiderive that with respect to y. And hopefully these should give me the same exact thing. Now, let's actually try to crank this through. For this first piece, you can split this apart, maybe set up some u substitution here, but you've probably seen the shortcuts or have, worked with these often enough to recognize, my antiderivative of my first component, hang on to y as a constant coefficient, but the antiderivative of 1 over x plus 5 is natural log of x plus 5. Over here, your antiderivative of this exponential function, you should get a minus e to the 3x, and then you should also get some sort of constant function on the end that's written in terms of y's. Now, for this other piece that should give you the same exact function back, if you are going to, antiderive this guy with respect to y, there's nothing but x's here, so I'm just going to slap a y on the front of this, okay? Now, in that particular case, we still get a constant of integration, but this time we have got some sort of constant function, but it's written in terms of x's, right? So these should be the same thing. These should totally be the same exact function here. I just need to reconcile this into one function, and some of the pieces actually come back as pretty obvious here. There should be a y times log x plus 5 expression in my potential function. There's no getting around that. It popped up in both pieces. We know it has to be there. The other thing that maybe I should expect is if I'm looking at my exponential term, that's a function of x, and I know that I'm supposed to get some sort of a function of x back here. There's going to be my function of x, okay? And if you have this, plus whatever on the end here, maybe there's an additional function of y, but I don't really see any additional y expressions down here, so at best, maybe there might have been some sort of constant that got tacked into the end. Because if you have a constant, it counts as either a function of x or a function of y, right? So at best, what happens when I go to reconcile this thing is this. You should expect to see a potential function that no doubt has this y natural log of x plus 5 term floating around. You definitely should see this e to the 3x, and, maybe we get a plus e on the end, maybe we don't, but for sake of computing with your fundamental theorem of line integrals, like I said, for actually applying that, we're going to leave this as optional. Now, why did I do this in the first place? Let's go back to the original problem statement. I'm trying to use my fundamental theorem of line integrals to evaluate this thing here, which is basically f dot dr. So if this expression is f dot dr, what the heck am I, really getting at here, right? So if I'm applying my fundamental theorem of line integrals, my original, f dot dr, okay, my given f, we just said that we should be able to express this, okay, this original integral as a line integral of a gradient, okay, so where this f, okay, is as above. And if I'm applying my fundamental theorem of line integrals, this basically says that you should be able to substitute in your endpoint and then substitute in your starting point and then take a difference, okay? And that's going to give you what the result is for your integral, okay? Now, just to kind of refresh, I'm going to scroll up for a moment to pull my RB and RA information. We said that the interval that this parameterization was relevant on was 1, 3. Okay, so this was 1 and 3 are my ending and starting points. So here, I've basically got f of r of 3 minus f of r of 1. And what in the heck was I substituting 3 and 1 into? Well, here I'm going to go ahead and pull my information on r. Okay, if I look at the r that I was using, the parameterization was 2t minus 6 comma t plus 1, okay? 2t minus 6, okay, so 2t minus 6, let me leave room for my f here, 2t minus 6, comma t plus 1, so, what's a t plus 1? Yeah, t plus 1. So t plus 1. Now over here, if I plug 1 into r, again, this is 2t minus 6, so 2t minus 6, comma t plus 1, so comma 1 plus 1. The things that I'm trying to substitute into r are going to look like f of, here, this will be 0, 4. And over here, this will be f of minus 4, 2. And now I just need to take these back to the potential function that we found. Okay, so the whole reason that we bothered trying to find some sort of little f, it was so I could know what to plug 0, 4 and minus 4, 2 into. Okay, so we said that that potential function was this guy right here. So plug in 0, 4, and subtract off what happens when you plug in minus 4, 2. Maybe I'll give myself a little bit of extra room here to evaluate this. If I plug in 0, 4, that's going to be 4 times natural log of 5 minus e to the 0. Here I'll go ahead and demonstrate why I told you guys the plus c is optional. I'll go ahead and throw it in. And then I'm going to subtract off what happens when I plug in minus 4, 2. So this will be 2 times natural log. Minus 4 plus 5 is natural log of 1. Minus e to the 3x. This will be minus 12. And then a plus c on the end. Now notice when I go to clean this all up, I've got a plus c minus a plus c. This is why I said for finding potential functions for these integrals, we don't really need to write those in. Additional things I can do to simplify here, log of 1 is 0. That term will drop off. And e to the 0 is 1. So if you want a finalized, tidied up answer, this is what we are looking at here. Okay? Now, I'm going to do one more example for you guys, and I will also close on this note. You notice I talked about this method for trying to figure out these 2D vector fields, when those things are conservative and when they're not. Now, there is a similar trick for using partials to check if a 3D vector field is conservative, but it's going to be a little bit messier. It's got a longer formula to it. There's a little bit more to that formula. We will see it again, but I'm going to put that off for a couple sections. Okay, so we're going to see the test for whether a 3D vector field is conservative using partials. We'll see that in section 16.5. For now, though, that method where we anti-derive to figure out what little f was, that still works, okay, regardless of how many dimensions our vector field lives in. So we're not going to worry about the partials bit. If I am asking you to use the fundamental theorem of line integrals to evaluate a line integral of a vector field and it's three-dimensional, we're going to go ahead and assume that I'm not asking you to try it for no reason. We'll actually assume this is conservative, so there should be some sort of function that you can find that serves as a potential for that vector field. Okay, so let's actually try this example here. I'm going into it assuming that this is conservative because I told you to use the fundamental theorem of line integrals to work with it. So that means we just get to jump right on in to basically figuring out what my antiderivatives are, right? So here I'm worried about my antiderivative of my first bit in my first component in my vector field with respect to x. I'm worried about my antiderivative of this second component with respect to y, and I will be worried about my antiderivative of my last component with respect to z. Okay, because again, if this was a conservative vector field, this looks like a gradient. That means this is fx, fy, fz. You have to antiderive with respect to z to undo that last partial. Okay, so hopefully all of these come out to the same thing, or at least we can reconcile these into the same thing, right? Now, if you antiderive this first bit with respect to x, here's what we're getting at. I'll go ahead and note we have a slightly different constant of integration. This time, there's two more variables to worry about. You might have gotten y in this function, but you might have also got some z's in here too, right? If you needed to check your work with the derivative, if you derive this guy with respect to x, the whole thing falls off and you still get the original integrand back, okay? Moving on, if I do my second bit, my antiderivative with respect to y, you notice that this e to the xy squared term pops up one more time, and my constant of integration this time, since I was antideriving with respect to y, maybe you might have had some x's and z's in here. Okay, and then the final piece here, I need an antiderivative with respect to z. You should expect 4 sine z here. Plus a constant of integration. Your constant is going to be a function, this time of x and y. So now what I'm looking to reconcile is, these are all supposed to be f, right? So these are all my same function, my same potential function, f. So what do I get to use for f if I try to piece all of those together? Well, notice, here's your function of x and y right here. And here's your function of z, which could fit either of these slots up top. Okay? So what I should expect in my f is that it does have to have an e to the x y squared in it, and it also has to have a plus 4 sine z in it. Okay, so this is my potential function. Now what that is telling me is my original line integral that I was asking for, my original f dot dr. So basically, you know, this thing right here, these are the same. What I'm looking at rewriting that as is, this is really a line integral of my gradient of f, where these guys are the same. So now I've got this line integral represented in terms of, a line integral of a conservative vector field. I should be able to express this thing, using my fundamental theorem of line integrals. I should be able to express this as f of r of b minus f of r of a. Okay? Now, comment on this. I didn't actually give you a parameterization this time. I just said, hey, the line segment from blah to blah. You can sit here and find a parameterization for that line segment and an interval that it works on, and you can plug in the a and b to your r and get the points back. Or we can just note exactly what I said before. These line integrals of conservative vector fields to path independent. What I'm really looking at here is f of an end point minus f of a start point. So I can make use of the fact that I named what the heck those points were, right? 0, 2 pi over 4 was my start point here, so I'm going to go ahead and fill that in. And my end point was this log 2 minus 1 pi over 2. Okay, so now I just get to sub these things into my potential function that I found, right? So I'll go ahead and give myself a little bit more room. We'll start over on the far left here. I needed e to the x y squared, so this will be e to the log 2 y squared plus 4 sine z, so plus 4 sine pi over 2. This is my first point evaluated in f, or my endpoint evaluated in f. And now I get to subtract off what happens when I plug in the second point. Again, e to the x, which is 0, times y squared, which is 2 squared, plus 4 times sine pi over 4. And now the rest of this is just going to be evaluation, okay? So first off, inverse functions, that'll simplify down to 2. Negative 1 squared is just going to be 1, so this first piece will be 2. We know that sine of pi over 2 is 1, so this first piece gives me an integer result. Over here for this second part, e to the 0 is 1, that'll basically drop off. 2 squared is going to be 4, and I still need 4 sine pi over 4, which would be root 2 over 2. Okay? If I'm cleaning this up on my way to a final answer, I can still note some of my cancellations, and end result, I should be getting 2 minus 2 root 2.